What if I told you the ground beneath your feet is more than just dirt and rock? It's a time capsule, a silent witness to Earth's most dramatic moments. Think about that for a second. Every step you take, every mountain you see, every canyon you admire, they're all part of a vast, layered archive, recording cataclysms that reshaped our planet long before humans walked its surface. This isn't just geology, it's detective work on a planetary scale, and the clues hidden in these layers, they reveal everything from towering tsunamis that swallowed continents to volcanic eruptions so massive they blotted out the sun for years. Now here's the mind-blowing part. These ancient disasters aren't just relics of the past. They hold urgent lessons for our future, because the same forces that sculpted Earth's history, asteroids, earthquakes, climate shifts, are still at work today. By peeling back the planet's layers like the pages of a book, scientists can spot patterns, predict risks, and even uncover warnings about what might lie ahead. It's as if Earth itself is whispering secrets to those who know how to listen. And in this video, we're going to learn its language. So let's begin this journey, not with a shovel, but with curiosity. Picture the deepest trenches, the tallest cliffs, the unassuming outcrops along a country road. Each one is a piece of the puzzle. From the ash that settled after a supervolcano's fury to the strange metals left by a dinosaur-killing asteroid, we'll explore how these layers form, what they tell us, and why they matter more than you might think. This isn't just about the past, it's about understanding the fragile, ever-changing world we call home. Ready to dig deeper? Let's go. The Earth's crust is more than just the ground we walk on. It's the planet's first chapter in a story of catastrophe. Imagine cracking open a rock and finding a layer of fine ash, like dust from an ancient fire. That's exactly what geologists do when they examine sedimentary deposits. These stacked layers of rock act as a timeline, preserving evidence of disasters that unfolded over millions of years. Take volcanic eruptions, for example. When a massive volcano explodes, it spews ash high into the atmosphere, which eventually settles and gets trapped between other layers of sediment. Centuries later, scientists can pinpoint the exact moment of that eruption, sometimes even matching it to historical records or ice core samples from thousands of miles away. But volcanoes aren't the only storytellers in the crust. Earthquakes leave their mark too, twisting rock formations into unnatural angles or creating sudden jumbles of debris where the ground violently shifted. And then there are the extraterrestrial visitors, meteorites. When a space rock slams into Earth, it scatters rare metals like iridium across the landscape, leaving a glittering fingerprint in the rock record. This is how researchers identified the impact that likely wiped out the dinosaurs, a thin, global layer of iridium-rich clay marking the end of an era. What makes these clues even more fascinating is how they connect across continents. The same ash layer from a single eruption might be found in Europe, Asia, and North America, linking distant regions through a shared moment of chaos. It's like piecing together a planetary jigsaw puzzle where every rock outcrop holds a fragment of the bigger picture. And as we decode these layers, we're not just learning about the past, we're uncovering patterns that could help predict future disasters. After all, the forces that shaped these ancient catastrophes haven't disappeared. They're still at work, quietly building the next chapter beneath our feet. Beneath the thin skin of the Earth's crust lies the mantle, a churning, restless ocean of rock that holds the keys to some of our planet's most violent transformations. This isn't just molten chaos, it's a dynamic system with rhythms and patterns that shape everything from towering mountain ranges to the very ground we stand on. Picture it like a pot of thick soup simmering on a stove where heat rises in slow, massive bubbles called mantle plumes. These plumes don't just move rock, they rewrite landscapes. Take Yellowstone, for example. Beneath its serene geysers and lush valleys lurks one of these colossal upwellings of heat, a remnant of past eruptions so powerful they blanketed entire continents in ash. The rocks here tell a story of cyclical fury, with evidence of massive eruptions occurring roughly every 600,000 years. And here's the unsettling part: we're statistically overdue for another. But before you panic, remember, geologists aren't just watching the clock. They're studying the subtle clues in igneous rocks, the cooled remnants of ancient magma, to decode the mantle's behavior. What makes these rocks so revealing? Unlike sedimentary layers, which record surface events, igneous rocks are direct snapshots of the mantle's composition and movement. When a volcano erupts, it's essentially sampling the mantle, bringing up material from depths we could never physically reach. By analyzing the chemistry of these rocks, scientists can trace plumes back to their source, almost like following a trail of breadcrumbs through Earth's interior. But the mantle's influence stretches far beyond volcanoes. Its slow, relentless motion is what drives tectonic plates, causing earthquakes and building mountains over millennia. Sometimes, these movements leave behind dramatic scars like the twisted bands of rock in the Himalayas, where continents collided with enough force to push seabed sediments to the top of the world. Other times, the mantle's work is more subtle, like the gradual sinking of entire regions due to shifting currents deep below. What's truly remarkable is how interconnected these processes are. A single mantle plume can trigger volcanic activity thousands of miles apart, while shifts in one tectonic plate can strain faults on another continent. It's a planetary domino effect, where events in Earth's hidden depths ripple outward with consequences we're only beginning to understand. And as we piece together these patterns, we're not just uncovering Earth's past, we're learning to read the whispers of its future. Deep beneath the mantle, at the very heart of our planet, lies a raging inferno of liquid metal, the Earth's core. This isn't just a static ball of iron and nickel. It's a dynamic engine, constantly in motion, generating the magnetic field that shields life from deadly cosmic radiation. But here's where things get eerie. That protective shield isn't always stable. Ancient lava flows hold a startling secret: tiny magnetic minerals frozen in time, their alignment telling us the planet's magnetic poles have flipped hundreds of times throughout history. And these reversals didn't just happen quietly. Some aligned chillingly with periods of mass extinction, as if the Earth itself momentarily lost its bearings. Picture this: the magnetic field weakens during a reversal, leaving the planet vulnerable to solar storms and cosmic rays. Without that invisible barrier, radiation could have bombarded the atmosphere, stripping away ozone and triggering catastrophic climate shifts. There's evidence this might explain sudden bursts of evolutionary change, like the rapid diversification of life after the Cambrian explosion, or conversely, the sudden disappearance of species during extinction events. One leading theory even suggests that weakened magnetism could have allowed more cosmic rays to reach the surface, increasing cloud cover and plunging the planet into cooling periods. Yet the core's influence doesn't stop there. Its turbulent convection currents don't just power the magnetic field, they also transmit energy upward, subtly influencing the mantle's movement. Some geophysicists argue that major shifts in core dynamics could trigger mantle plumes, setting off chains of volcanic activity that reshape continents. It's a domino effect from the planet's deepest layers. A hiccup in the core might destabilize the mantle, which in turn fractures the crust, leading to eruptions, earthquakes, or even rapid climate swings. What makes this especially fascinating is how recent discoveries challenge old assumptions. For decades, scientists thought geomagnetic reversals took thousands of years, slow, gradual processes. But now, studies of ancient pottery and volcanic rocks suggest some flips might have happened in mere decades. Geological blink of an eye. Imagine living through that, compasses spinning wildly, auroras appearing at the equator, and an unseen cosmic storm brewing overhead. While we're still unraveling the full impact of these events, one thing is clear: the core isn't just a distant curiosity. It's a silent architect of catastrophe, its rhythms echoing through every layer of the planet, from the deepest trenches to the highest peaks. And as we learn to read its language, we're uncovering not just Earth's past, but clues to its unpredictable future. Sedimentary layers are like Earth's own history books, written not in ink but in stone, ash, and the remnants of life itself. Each stratum tells a story, sometimes quiet and slow, other times violent and abrupt. Take the infamous KPG Boundary, that thin, global line of clay marking the end of the Cretaceous period. To the naked eye, it might seem unremarkable, but packed within it are clues to one of the most devastating events in our planet's history. That layer is laced with iridium, a metal rare on Earth's surface but abundant in asteroids. Its presence was the smoking gun that helped scientists confirm a colossal space rock struck the planet 66 million years ago, triggering wildfires, tsunamis, and a years-long winter that doomed the dinosaurs. But it's not just asteroids that leave their mark. Volcanic eruptions paint the rock record too. When Mount Tambora exploded in 1815, its ash circled the globe, chilling the climate so drastically that the following year became known as the year without a summer. Crops failed, frosts came in July, and the skies turned eerie shades of red and orange, all of it captured in sediment layers from Europe to North America. Even more dramatic are the flood basalts, like the Deccan Traps in India, where lava flows piled up miles thick over centuries, releasing enough greenhouse gases to trigger mass extinctions long before the asteroid arrived. Then there are the quieter disasters, the slow-motion catastrophes recorded in layers of fossilized mud or sand. In the American Southwest, ancient lake beds hold evidence of megadroughts that lasted decades, turning lush landscapes into deserts. Along coastlines, sediment cores reveal sudden jumps in sea level, entire civilizations swallowed by rising waters, their stories preserved in layers of silt and shell. What's astonishing is how precise these archives can be. By matching chemical signatures, fossil sequences, and even microscopic particles, scientists can correlate layers across continents, piecing together a global timeline of disaster. A single ash deposit from a supervolcano in Indonesia might be found in Antarctic ice cores, Greenland sediments, and African lake beds, linking distant events into a single, coherent narrative. And as we learn to read these layers more carefully, we're not just uncovering the past, we're finding eerie parallels to the challenges we face today, from climate shifts to the threat of future impacts. The Earth's archives are always speaking. The question is, are we listening? Volcanic ash isn't just dust on the wind, it's a geological signature, a calling card left behind by Earth's most violent outbursts. When a volcano like Tambora or Krakatoa erupts, it doesn't just reshape the local landscape, it catapults millions of tons of fine ash and sulfur dioxide high into the stratosphere, where winds carry it around the globe. These particles don't settle quickly. They linger for years, scattering sunlight and cooling the planet beneath them. We've seen this play out in recent history, like the 1991 eruption of Mount Pinatubo, which dropped global temperatures by nearly 1 degree Celsius for 2 years. But scale that up to something like the Deccan Traps, a series of eruptions in ancient India that lasted hundreds of thousands of years, and you're talking about climate disruption on a whole other level. The rocks tell the story. In India's Deccan region, those stacked lava flows stretch taller than skyscrapers in places, a monument to volcanic fury. But it's not just the sheer volume of lava that made these events catastrophic. It's what the eruptions pumped into the air, sulfur transformed into acid rain, scorching vegetation and poisoning waterways. Carbon dioxide built up over centuries, triggering runaway greenhouse effects after the initial cooling faded. And the ash, it didn't just block sunlight, it smothered entire ecosystems under sterile gray blankets. Fossil records from this period show staggering drops in biodiversity, with some species vanishing abruptly while others struggled through centuries of ecological chaos. Now compare that to the Siberian traps, another epic volcanic event 250 million years ago. Here, the eruptions were so vast they may have helped trigger the Great Dying, the worst mass extinction in Earth's history, wiping out 96% of marine species and 70% of land vertebrates. The clues are in the chemistry. Rock layers from this period show wild spikes in mercury, a toxic byproduct of volcanic emissions. There's evidence of oxygen-starved oceans turning murderously acidic, while land temperatures swung violently between extremes. It's a chilling parallel to today's climate concerns, just on a geological timescale. What makes these ancient disasters so relevant now is their eerie resemblance to human-caused climate shifts. The mechanisms are different, but the outcomes have similar hallmarks: rapid temperature changes, ocean acidification, ecosystem collapse. By studying how life recovered after these volcanic apocalypses, scientists can glimpse potential paths forward for our own changing world. Some species adapted, others migrated, many simply vanished. The ash layers preserving these events aren't just geological curiosities. They're cautionary tales written in stone, reminding us that while Earth's systems are resilient, they have breaking points. And once crossed, the road back can be unimaginably long. Imagine plunging a straw a mile deep into Antarctica's ice and pulling up a frozen timeline of Earth's most dramatic moments. That's essentially what scientists do when they extract ice core cylinders of ancient ice packed with secrets. These pristine records, drilled from the glaciers of Greenland and Antarctica, are like nature's own hard drives, storing data about everything from volcanic eruptions to industrial revolutions. Unlike rocks or sediment, ice captures snapshots of the atmosphere itself, trapping tiny bubbles of ancient air in its crystalline grip, one of the most startling discoveries hidden in these icy layers. The speed at which climate can shift. Take the Younger Dryas period around 12,000 years ago. Ice cores reveal that global temperatures plummeted by up to 10 degrees Celsius in just decades, a geological blink of an eye. This wasn't a gradual cooling, it was a climate free fall, likely triggered by a sudden shutdown of ocean currents. Forests turned to tundra, megafauna vanished. And the ice tells us it happened faster than we once thought possible. But it's not just temperature these cores measure. Volcanic ash layers stand out like dirty fingerprints in the ice, marking eruptions that rocked the planet. When Iceland's Laki volcano erupted in 1783, its sulfur dioxide haze drifted across Europe, recorded in Greenland's ice as a spike in acidity. That same haze brought famine, killing crops and livestock as far away as Egypt. Even more dramatic are the traces of asteroid impacts, like the platinum-rich dust linked to a cosmic collision that may have triggered a mini ice age 13,000 years ago. What makes ice cores uniquely powerful is their precision. Each year's snowfall compresses into a distinct layer, creating a timeline so accurate scientists can pinpoint events down to the season. Meltwater from a summer heatwave, it's there. Lead pollution from ancient Roman smelters, detected. the radioactive fallout from 20th century nuclear tests. Preserved like a cautionary postscript, perhaps most sobering are the recent layers where human influence becomes unmistakable. Carbon dioxide concentrations, stable for 800,000 years, now spike off the charts. Soot from factories, chemicals from plastics, they're all frozen into the record, a stark ledger of our impact. Yet these cores also offer hope. They show Earth's resilience. After past catastrophes, the planet eventually found equilibrium. The question is whether we'll learn from these frozen lessons before we write the next catastrophic chapter ourselves. Fossils don't just tell us what lived, they reveal how life died. Buried within the Earth's layers are snapshots of moments when entire ecosystems collapsed with startling speed. Take the Permian-Triassic boundary, a thin band of rock marking the worst catastrophe life has ever faced. Known as the Great Dying, this event wiped out 96% of marine species and 70% of land vertebrates in what geologically amounts to a heartbeat. The fossils here aren't just scarce, they're chaotic. Coral reefs that thrived for millions of years suddenly vanish, replaced by mats of bacteria that flourished in the toxic, oxygen-starved waters left behind. On land, reptile skeletons are found tangled together in death poses, as if frozen mid-flight from some invisible calamity. What makes these fossilized graveyards so haunting is the sheer abruptness they capture. In places like the Karoo Basin in South Africa, paleontologists find layers teeming with diverse Permian-era fossils lumbering dicynodonts, sleek gorgonopsians, only to hit a horizon where everything disappears. Above that line, a barren wasteland of scraggly survivors and opportunistic fungi. There's no gradual decline, no slow fade into extinction, just a before and after, separated by what might have been as little as 50,000 years, a blink in geological time. The culprit, clues point to a 1-2 punch of catastrophic volcanism and climate chaos. Siberian traps eruptions, which lasted for hundreds of thousands of years, pumped enough carbon dioxide into the atmosphere to trigger runaway global warming. Oceans turned lethally acidic, while land temperatures soared to desert-like extremes. But here's the twist. Fossilized pollen tells us vegetation collapsed before the worst of the volcanic activity. That suggests the planet's systems were already teetering on the edge, a warning for today's ecosystems under stress from human activity. Yet even in these dire records, there are glimmers of resilience. Burrowed fossils show some species, like the humble Lystrosaurus, survived by adapting to harsh new conditions. These hardy generalists became the ancestors of future life, proof that catastrophe can rewrite evolutionary rules overnight. The lesson: Earth's history isn't just a series of slow changes. It's punctuated by moments of violent transformation, where the fate of species hinges on the planet's most turbulent chapters. And as we uncover these ancient tragedies, we're reminded that stability is never guaranteed. It's something life must continually earn. The ground beneath our feet isn't as solid as it seems. It's more like a jigsaw puzzle with pieces that never stop moving. These tectonic plates, massive slabs of Earth's crust, slide, collide, and grind against each other at speeds comparable to fingernail growth. But don't let that slow pace fool you. Over millions of years, these incremental movements build mountains, carve oceans, and unleash disasters that reshape continents. Take the Himalayas, the planet's tallest mountain range. This towering wall of rock wasn't sculpted by erosion alone. It's the crumpled wreckage of an epic collision between the Indian and Eurasian plates, a slow-motion crash that began 50 million years ago and still continues today. Every year, India creeps northward by about 2 inches, shoving the Himalayas higher and triggering earthquakes that ripple across Asia. But it's not just collisions that spell trouble. Where plates pull apart, like along the mid-Atlantic ridge, magma surges upward to form new crust, a process that seems peaceful until you realize it fuels volcanic hotspots like Iceland. Then there's the sideways grind of transform boundaries, where plates scrape past each other with terrifying friction. California's San Andreas Fault is a prime example, a seam in the Earth where the Pacific Plate inches northwest against the North American Plate. When that tension finally snaps, the result is earthquakes like the one that leveled San Francisco in 1906. What makes these boundaries so dangerous is their unpredictability. Unlike volcanoes, which often give warning signs like tremors or gas emissions, earthquakes can strike with little to no preamble. The 2004 Indian Ocean tsunami, which killed over 200,000 people, was triggered by a megathrust earthquake along the Sunda Trench, a subduction zone where the Indian Plate dives beneath the Burma Plate. In moments, 1,000 miles of seafloor lurched upward, displacing enough water to send waves racing across entire oceans. Yet for all their destructive power, tectonic movements also create the very conditions that make life possible. Subduction zones recycle carbon back into the mantle, regulating Earth's climate over eons. Volcanic arcs enrich soil with minerals, fostering agriculture. Even earthquakes play a role, fracturing rock to release groundwater into arid regions. The same forces that bring catastrophe also sustain ecosystems, a paradox written into the planet's DNA. Today, scientists monitor these restless boundaries with satellite networks and seismic arrays, searching for patterns that might predict the next big rupture. From the Cascadia subduction zone off North America's west coast, where a magnitude 9 quake is overdue, to the simmering tension beneath Istanbul's crowded streets, the lessons of plate tectonics are clear. Earth's surface is a dynamic, ever-changing mosaic. And while we can't stop the plates from moving, understanding their rhythms might just help us prepare for the chaos they bring. Picture a volcano, but not the towering, cone-shaped kind. Instead, imagine cracks in the earth stretching for miles, fountains of molten rock erupting in endless curtains of fire. This is the terrifying reality of flood basalts, volcanic events so massive they drown entire landscapes in lava, not over days but centuries. The Columbia River Plateau in the Pacific Northwest is a haunting example. A region the size of Washington state buried under layer after layer of hardened lava, some flows stretching over 400 miles from their source. To walk across this landscape today is to tread on the aftermath of eruptions that released enough lava to fill Lake Erie 30 times over. What makes flood basalts truly apocalyptic isn't just the lava, it's what they pump into the air. These eruptions are relentless, spewing sulfur dioxide and carbon dioxide for thousands of years without pause. The Deccan Traps in India, another flood basalt region, may have released more greenhouse gases in 50,000 years than humanity has in centuries of burning fossil fuels. The result, a climate roller coaster. First, sulfur aerosols blot out the sun, triggering a volcanic winter. Then, as those particles settle, the accumulated carbon dioxide takes over, baking the planet in a greenhouse effect that can last for millennia. The fossil record bears witness to the devastation. Marine sediments from flood basalt eras show stark chemical shift, spikes in mercury, drops in oxygen, and the telltale signatures of acidified oceans. Coral reefs collapse, shellfish struggle to form their skeletons in the corrosive waters. On land, pollen fossils reveal sudden shifts from diverse forests to monotonous stands of ferns, nature's disaster weeds. It's no coincidence that the Siberian Traps eruptions align with the Permian extinction, or that the Deccan Traps overlap with the demise of the dinosaurs. These weren't just bad days for life on Earth, they were planetary resets. Yet amid the destruction, flood basalts also hold clues to Earth's resilience. In the Columbia Plateau's wake, soils enriched by volcanic minerals eventually gave rise to some of North America's most fertile farmland. And while the initial eruptions were catastrophic, the long-term release of carbon dioxide may have helped pull the planet out of earlier ice ages. It's a paradox. The same forces that bring ruin can also set the stage for renewal. Today, scientists study these ancient lava floods like cautionary tales. While we're unlikely to face a flood basalt event in our lifetimes, their mechanics mirror humanity's own impact on the climate, just sped up the difference. We have something the volcanoes didn't: foresight. By decoding these layers of stone and gas, we're learning how to read Earth's warning signs, and perhaps how to avoid writing another chapter in its book of catastrophes. 66 million years ago, a rock the size of Mount Everest slammed into what's now the Yucatan Peninsula with the force of 1 billion nuclear bombs. The Chixilub impact didn't just leave a crater, it rewrote the rules of life on Earth. But what makes this event so chilling isn't just the immediate devastation. It's the chain reaction of disasters that followed. The initial explosion vaporized rock, sending superheated debris raining back down, igniting wildfires across continents. Then came the dust. Trillions of tons of pulverized stone kicked into the atmosphere, blotting out the sun for years. Photosynthesis ground to a halt. Temperatures plummeted, and in the darkness, 75% of all species perished, including the non-avian dinosaurs that had ruled for 160 million years. Yet Chixilub isn't alone in Earth's impact history. Scattered across the globe are other, older craters with their own tales of catastrophe. In South Africa, the Vredefort crater, twice as wide as Chixilub, bears witness to a 2-billion-year-old impact so violent it likely vaporized shallow oceans. Then there's Siberia's Popogai crater, where a strike 35 million years ago may have accelerated an already unfolding ice age. Even smaller impacts leave forensic traces, like the iridium-rich layer found in Italian riverbeds from a half-mile-wide asteroid that exploded over Europe just 14,000 years ago, possibly contributing to the extinction of mammoths and other ice age giants. What's startling is how often these events recur. Geologists estimate that asteroids large enough to cause global disruptions, objects over half a mile wide, hit Earth roughly every 500,000 years. And while that might sound rare, consider this: humanity's entire written history spans just 5,000 years. Statistically, we're living on borrowed time. But here's where modern science changes the game. Unlike dinosaurs, we can see these threats coming. Networks like NAS, a Planetary Defense Coordination Office, now track over 20,000 near-Earth objects, calculating their orbits centuries in advance. Some, like the infamous Apophis asteroid, once deemed a serious threat for 2029, have been ruled out after precise observations. Others remain on the watch list. And for the first time in history, we're not just watching, we're testing defenses. Missions like DART have proven we can nudge an asteroid's trajectory, potentially averting disaster. The lesson written in Chixilub's fractured rocks isn't just about past destruction. It's about resilience, how life bounces back, how mammals rose from the ashes of dinosaur dominance. But it's also a warning: cosmic threats are inevitable. The difference now is that we're no longer passive victims of celestial chance. We're the first species capable of reading the sky and rewriting our fate. Supervolcanoes aren't your typical mountains. They're sprawling, simmering calderas capable of unleashing destruction on a scale that dwarfs ordinary eruptions. Yellowstone, perhaps the most famous of these sleeping giants, last erupted 630,000 years ago, blanketing North America in ash and altering global temperatures for decades. But here's what most people don't realize: Yellowstone isn't unique. beneath Indonesia's Lake Toba lies another supervolcano, one that erupted 74,000 years ago with such force it may have reduced the human population to just a few thousand survivors. The ash from that event has been found as far away as the South China Sea, a testament to its planet-shaking power. When a supervolcano erupts, it doesn't just spew lava, it obliterates the landscape in a pyroclastic surge, then pumps millions of tons of sulfur dioxide into the stratosphere. This gas transforms into reflective aerosols, wrapping the planet in a sun-blocking shroud. The result, a volcanic winter. Tree rings from the year 536 reveal a period of stunted growth linked to a massive eruption, possibly from Ilopango in El Salvador, that brought frost in July and crop failures across Europe and Asia. Historical records from the time describe a sun that gave no more light than the moon, a haunting glimpse of what a Yellowstone-scale event could unleash today. Yet the real danger isn't just the immediate aftermath, it's the domino effect. Ashfall destroys farmland, poisoning soil and choking livestock. Global food chains collapse as sunlight dims, triggering mass migrations and wars over dwindling resources. The eruption of Tambora in 1815 offers a sobering preview. Famines in China, typhus outbreaks in Europe, and the infamous Year Without a Summer that inspired Mary Shelley's Frankenstein during a dreary Swiss vacation. And Tambora was a mere hiccup compared to Yellowstone's potential. Modern monitoring offers some hope. Networks of seismometers and GPS stations now track the slightest bulges or tremors in volcanic hotspots. At Yellowstone, scientists measure the rising and falling of the land itself, sometimes by as much as 10 inches per year, as magma shifts beneath the surface. Satellites sniff for trace gases that might signal unrest, but preparedness remains our greatest defense. Unlike asteroids, supervolcanoes give warnings, subtle, slow building clues that could buy us crucial time to stockpile food, reinforce infrastructure, or even attempt radical interventions like drilling to relieve magma pressure. What makes these giants especially unnerving is their cyclical nature. Yellowstone erupts roughly every 600,000 years like clockwork. We're statistically overdue. Yet uncertainty lingers, not if, but when. And when that day comes, the layers of ash it leaves behind won't just be geological curiosities. They'll be pages in a survival manual for whatever civilization rises next. Beneath the ocean's surface lies one of Earth's most chilling archives, thick layers of black shale that tell the story of times when the seas turned toxic. These sinister deposits, found in sediment cores from the Atlantic to the Pacific, aren't just dark in color. They're stained by the remains of ancient marine life that suffocated when oxygen vanished from the water. Scientists call these catastrophic periods oceanic anoxic events, and they've happened multiple times throughout Earth's history, each one a warning written in stone about how quickly thriving ecosystems can collapse. The most infamous of these events unfolded during the Cretaceous period, around 94 million years ago. Volcanic activity from the Caribbean Large Igneous Province, a colossal outburst of molten rock, spewed greenhouse gases into the atmosphere, warming the planet and slowing ocean currents. As surface waters heated up, they became less dense, forming a stagnant lid that prevented oxygen from mixing into the depths. Marine life below this barrier suffocated en masse. Their decaying bodies fed bacteria that released hydrogen sulfide, turning vast stretches of the ocean into toxic dead zones. The evidence is etched into those black shale layers. Fossils of bottom-dwelling creatures abruptly vanish, replaced by mats of sulfur-loving microbes that thrived in the poison. What makes these events so alarming is their eerie resemblance to modern threats. Today, warming oceans and agricultural runoff are already creating smaller-scale dead zones. like the one in the Gulf of Mexico that grows larger than Connecticut every summer. While we haven't reached the global catastrophe of ancient anoxic events, the ingredients are disturbingly similar: rising temperatures, sluggish currents, and excess nutrients fueling algal blooms that choke off oxygen. The difference this time, the trigger isn't volcanoes, it's us. Yet buried in these dark layers are also glimmers of hope. After each anoxic event, the oceans eventually recovered, not overnight, but over millennia. Some species adapted, evolving to tolerate lower oxygen levels. Others migrated to refuges where conditions remained tolerable. The shale itself tells this story of resilience, gradually lightening in color as oxygen returned and life repopulated the depths. The lesson isn't just about past disasters, it's a roadmap. By studying how ancient oceans crossed and eventually reversed these deadly thresholds, scientists gain clues about how to protect our seas today. Reducing nutrient pollution, curbing carbon emissions, and safeguarding marine corridors could buy time for ecosystems to adapt. The black shale layers are more than geological oddities. They're a challenge from the past, asking if we'll heed their warning before the oceans write another chapter in their book of dead zones. Scattered across landscapes from the plains of North America to the hills of Scandinavia, there are boulders that don't belong. These massive rocks, some as big as houses, sit perched on bedrock that doesn't match their composition, stranded like forgotten luggage from a journey taken millennia ago. These are glacial erratics, and they're not just geological oddities. They're the fingerprints of ice sheets that once smothered continents, carrying these stones hundreds of miles before abandoning them when the climate shifted. Take the famous Madison Boulder in New Hampshire, a 5,000-ton block of granite resting atop completely different bedrock. Its sheer size defies logic until you realize it was plucked from the White Mountains by a glacier 20,000 years ago and dragged like a pebble in a frozen river. Or the Okotoks Erratic in Alberta, a 15,000-ton quartzite slab that ice transported all the way from the Canadian Rockies. These boulders didn't just tumble downhill. They were passengers on a one-way trip aboard moving walls of ice, some traveling farther than the distance between New York and Chicago. But erratics do more than mark ancient ice highways. They reveal the sheer violence of glacial movement. Many bear deep scratches called striations, gouges left as the ice dragged them across bedrock like sandpaper. Others are polished smooth on one side, shaped by centuries of grinding against the glacier's belly. Some even shattered mid-journey, their fragments scattered like breadcrumbs along the ice's path. Each mark tells a story of force, of landscapes being reshaped by ice that could move mountains literally. Perhaps most fascinating is what these stones say about climate chaos. Erratics often cluster in terminal moraines, piles of debris marking where glaciers stalled before retreating. These sudden stops weren't gradual. Ice cores and sediment records show that the end of ice ages wasn't a slow thaw, but a series of violent oscillations. Warm periods called interstadials could spike temperatures by 10 degrees Celsius in decades, causing glaciers to surge forward or collapse backward in geological moments. The erratics they dropped became mileposts of these climate whiplashes, frozen in place when the cold suddenly returned or the heat won out. Today, scientists use these misplaced boulders like puzzle pieces. By tracing their mineral signatures back to parent bedrock, they map the flow of vanished ice sheets with startling precision. Some erratics even carry microscopic hitchhiker's pollen or volcanic ash trapped in their crevices that reveal what the world looked like when they fell from the melting ice. In a way, these stones are time capsules, preserving snapshots of ecosystems long gone. Yet their most sobering lesson is one of impermanence. The same forces that stranded these boulders' climate shifts we now know were triggered by orbital cycles and atmospheric changes are still at work today. As Greenland's ice sheet retreats, it's leaving behind modern erratics, fresh markers of a new climate chapter. The difference this time, the hand moving the ice isn't just nature's. It's ours, and the stones we leave for future geologists might tell a very different story. Deep within volcanic rocks and ancient clay lies a hidden compass, one that doesn't point north but backward through time. When lava cools or sediment settles, tiny magnetic minerals within it lock into place, aligning with Earth's magnetic field like microscopic needles frozen in a moment. This phenomenon, called paleomagnetism, reveals something astonishing. Our planet's magnetic poles have swapped places hundreds of times, with north becoming south and vice versa. These reversals aren't gentle transitions. They're chaotic events where the magnetic field weakens dramatically, sometimes for centuries, leaving life exposed to cosmic radiation that normally deflects harmlessly into space. Take the Lashump excursion, a brief flip that occurred 41,000 years ago. Ice cores from that period show a spike in radioactive beryllium-10, an isotope produced when cosmic rays bombard the atmosphere. At the same time, cave paintings from France and Australia depict eerie red auroras, normally confined to polar regions, suggesting the weakened magnetosphere allowed solar storms to ignite skies worldwide. Even more telling are the fossil records. The Lashump event coincides with the extinction of Australia's megafauna and Neanderthal decline in Europe, hinting that prolonged radiation exposure might have played a role. But the most chilling correlation lies deeper in the rock record. The Matayama Brun's reversal 780,000 years ago lines up with a mass die-off of marine microorganisms. Sediment layers show these tiny creatures thrived for millions of years, until their fossilized shells suddenly exhibit deformities, as if bathed in mutagenic rays. Meanwhile, on land, pollen records reveal abrupt shifts in plant communities, with sun-sensitive species vanishing as UV levels soared. What makes these magnetic flips so destabilizing isn't just the loss of navigation cues for migrating animals, though that's part of it. It's the cascade of effects. A weakened magnetosphere allows solar winds to strip away atmospheric gases, potentially thinning the ozone layer. Increased radiation could trigger cloud formation, altering weather patterns. Some scientists even speculate that cosmic rays might influence mutation rates, accelerating evolutionary change during these turbulent periods. Yet here's the twist: we're long overdue for another reversal. The average interval between flips is 250,000 years, and the last one was nearly 800,000 years ago. Satellites now detect troubling signs. The magnetic field is weakening 10 times faster than expected, with a particularly unstable zone called the South Atlantic anomaly already disrupting spacecraft electronics. But unlike the dinosaurs, we have tools to adapt. Deep underground, mineral-rich caves could shield sensitive ecosystems. Satellites can be hardened against radiation. And by decoding the magnetic whispers in ancient rocks, we're learning to read the next chapter before it's written. The story of paleomagnetism isn't just about poles flipping. It's a reminder that Earth's protective shields are fragile, and that the same forces that shaped life's darkest hours might also hold the keys to our survival. High above today's shoreline, nestled among layers of ancient soil, lie sheets of coarse sand and shell fragments where they have no right to be, trapped between deposits of fine silt and clay that speak of quiet centuries. These anomalous layers are geological smoke alarms, signaling moments when towering walls of water roared far inland, scouring coastlines clean before dumping their stolen sediment in chaotic heaps. The Storegga slide deposits along Norway's coast tell one such horror story. Around 8,200 years ago, an undersea landslide the size of Iceland sent cubic miles of continental shelf crashing into the abyss. The resulting tsunami didn't just ripple, it rampaged, sending waves over 80 feet tall screaming across the North Sea. You can still walk the evidence today. In eastern Scotland, researchers have traced sand sheets filled with marine microfossils 20 miles inland, stranded like flotsam from some impossible tide. Dig deeper, and the layers grow more disturbing boulders the size of cars perched atop cliffs, their mineral fingerprints matching seabed rocks miles offshore. These aren't just rocks, they're receipts from nature's most violent shopping spree, where waves plucked entire cliffs and delivered them inland like grotesque gifts. But it's not just landslides that leave these calling cards. Japan's Jogan tsunami of 869 left sand sheets under present-day Sendai that precisely mirror the patterns of the 2011 Tohoku disaster, proof that catastrophic waves strike the same coast in eerily similar intervals. Even more chilling are the ghost forests of the Pacific Northwest, where stands of drowned cedars mark sudden land subsidence during megaquakes, their roots poisoned by saltwater as the coast dropped 6 feet in minutes. The sand layers beneath these dead trees, tsunami deposits from the same event dating back to the year 1700. What makes these deposits so vital is their forensic detail. Unlike earthquake faults or volcanic ash, tsunami layers record the wave's behavior, how far it reached, how fast it moved, even how many pulses crashed ashore. In Thailand, the 2004 Indian Ocean tsunami left distinctive inundation carpets of sand and coral fragments that helped model future risks. Along Chile's coast, successive tsunami deposits show a pattern. Every 300 to 500 years, the land gets hammered by waves from megaquakes along the same fault segment. The lesson written in these sand layers isn't subtle. From the cascading failures of underwater landslides to the pent-up fury of subduction zones, the triggers for these disasters haven't disappeared, they're just biding their time. Modern sonar maps reveal fresh scarps where continental shelves could collapse tomorrow. GPS networks show tectonic plates straining against each other, storing energy for the next great rupture. The difference now is that we can read the warnings if we choose to listen, because when the next tsunami's deposits form, they'll write their story not just in sand, but in the rubble of our complacency. Limestone isn't just another rock, it's a library of Earth's climate history, written in the language of shells and coral. Picture the white cliffs of Dover, those towering walls of chalk that glow in the sunlight. What you're seeing isn't just stone, it's the compressed remains of countless tiny sea creatures that thrived in warm, shallow oceans millions of years ago. Each layer is a page in a climate diary, capturing moments when the planet's thermostat swung wildly between extremes. Take the limestone formations in Italy's Apennine Mountains, where geologists have found alternating bands of dark and light rock. The dark layers are packed with organic material, evidence of times when the oceans were starved of oxygen, suffocating marine life and preserving their remains in eerie detail. The lighter layers, they're crammed with fossilized plankton that flourished when seas were rich with nutrients and sunlight. Together, these stripes tell a story of booms and busts, of oceans that veered between paradise and graveyard. But here's where it gets even more fascinating. Some limestone layers aren't gradual, they're abrupt. In the Bahamas, there are underwater cliffs where pristine coral reefs suddenly give way to jagged boulders, as if a switch was flipped. These chaotic deposits line up with periods of rapid sea level rise, when melting ice sheets drowned coastlines faster than reefs could grow upward. Elsewhere, Limestone packed with tropical fossils sits atop glacial debris, a contradiction that reveals how quickly climates have lurched from icehouse to greenhouse in the past. The real smoking guns, though, are the chemical fingerprints hidden in these rocks. Limestone contains isotopes of oxygen that act like tiny thermometers, revealing the temperature of the water when the rock formed. By analyzing these ratios, scientists have uncovered spikes in global temperatures so sudden they make today's warming look sluggish. One such spike, 56 million years ago during the Paleocene-Eocene thermal maximum, saw oceans heat by 8 degrees Celsius in just a few thousand years, a blink in geological time. The limestone from this period tells a harrowing tale. Shells grew thinner, species vanished, and acidic waters dissolved entire ecosystems. What makes these ancient climate swings so urgent is their resemblance to modern trends. Like today, many were triggered by massive carbon releases, not from burning fossil fuels, but from volcanic activity or methane bubbling up from seafloor deposits. The difference: nature took thousands of years to pump out the carbon we've released in centuries. Yet the aftermaths were eerily similar: rising seas, oxygen-starved oceans, and mass extinctions. Limestone's greatest lesson isn't just about the past. It's a mirror reflecting the consequences of rapid change and a warning that the planet's memory is longer than our own. Those quiet white cliffs, they've seen this story before. The question is whether we'll heed its ending. Buried beneath layers of shale and sandstone, coal seams hold a paradox. They're both monuments to life and harbingers of catastrophe. These thick black bands of compressed plant matter didn't form gradually over centuries. They're snapshots of entire ecosystems frozen in time, capturing moments when lush forests were abruptly swallowed by the Earth. The Carboniferous Period, 300 million years ago, was the ultimate greenhouse world, a time when towering tree ferns and giant horsetails thrived in steamy swamps that stretched across continents. But what turned these vibrant jungles into the coal that powers our modern world? A perfect storm of geological violence. Imagine a coastal forest thriving in the muggy Carboniferous air. Suddenly, rising sea levels flood the land, drowning trees in sediment-laden water that starves them of oxygen. Without decay, the organic matter piles up layer upon layer of fallen leaves, branches, and trunks. Then tectonic forces shift, plunging these soggy graveyards deeper underground where heat and pressure work their alchemy. Over millennia, the molecular structure of the plants transforms, squeezing out water and volatile gases until only carbon remains. But here's the twist: these weren't gentle transitions. Coal seams often show sudden boundaries. One moment you're looking at fossilized tree roots still standing upright, the next you're staring at barren shale. These sharp divides tell us these forests didn't fade away. They were buried alive. The Illinois Basin in North America reveals this drama in stark detail. Some coal seams here stretch over 10 feet thick, representing thousands of years of plant growth. Yet drill cores show these organic layers sandwiched between marine sediments, proof that rising oceans repeatedly drowned the swamps. Similar patterns appear in Europe's Ruhr Valley, where coal beds alternate with river deposits, suggesting cycles of flooding and regrowth. But the most telling clues come from coal balls, lumps of petrified peat that preserve the original forest floor. Slice one open, and you'll find leaves still attached to branches, fungi mid-feast on decaying wood, even the delicate wings of ancient insects. These time capsules confirm the burial was sudden, freezing ecosystems in their prime. What makes these seams so ominous isn't just their violent origins, it's what they represent for our future. The Carboniferous was a world of extremes, with atmospheric oxygen levels reaching 35% compared to today's 21%. This supercharged air-fueled wildfires that left charcoal traces in coal layers, while the abundant plant life sucked so much carbon dioxide from the atmosphere that it triggered an ice age. Sound familiar? Our current climate crisis is essentially the Carboniferous in reverse. We're burning those ancient forests and releasing their stored carbon back into the skies at a breakneck pace. The lesson in these blackened rock layers is clear. Stability is an illusion. The same forces that turned Carboniferous jungles into coal-rising seas, shifting landscapes, atmospheric chaos are still at work today. Only now, we're not just witnesses to the change, we're the ones turning the page. Beneath the Mediterranean Sea lies a geological mystery, a layer of salt 2 miles thick, stretching across an area larger than Texas. This isn't just ordinary table salt. It's the ghost of an ancient ocean that vanished almost overnight. 6 million years ago, the Mediterranean became a bathtub with no drain. Tectonic shifts sealed the Strait of Gibraltar, cutting off the Atlantic's flow. Under the scorching sun, seawater evaporated faster than rain could replenish it. Within 1,000 years, a heartbeat in geological time, the Mediterranean shrank into a series of hyper-salty lakes, leaving behind towering cliffs of crystallized salt where whales once swam. These evaporite deposits aren't just relics of the past, they're time capsules of climate chaos. Drill cores reveal the salt isn't uniform. It's layered like a cake, with bands of gypsum and potassium salts sandwiched between dusty remnants of dead microorganisms. Each stripe tells a story, years of relentless evaporation, followed by sudden floods when the Atlantic briefly broke through, then more drying. The sheer volume is staggering. Some layers would take modern evaporation ponds centuries to reproduce. Yet the Mediterranean basin didn't just dry once. Evidence suggests this cycle repeated dozens of times, with sea levels yo-yoing by hundreds of feet. The environmental toll was catastrophic. As water vanished, oxygen-starved death zones expanded, suffocating marine life. Land animals migrating across the exposed seafloor faced salt flats hotter than Death Valley, their footprints preserved in mineral crusts. Then, 5 million years ago, disaster struck in reverse. The Atlantic finally burst through Gibraltar with the force of 1,000 Amazons, refilling the Mediterranean in what geologists call the Zanclean flood. The cascade of water carved canyons deeper than the Grand Canyon in weeks, drowning the salt pans under a roiling new sea. Today, similar drying threats loom, not from tectonic shifts but human hands. The Aral Sea, once the world's 4th largest lake, has shrunk to 1/10 of its size due to irrigation demands, leaving rusted shipwrecks stranded in salt deserts. The Dead Sea drops 4 feet yearly as rivers are diverted. Even the Great Salt Lake faces collapse, its drying bed releasing toxic arsenic dust into the wind. The lesson from ancient evaporites is clear. When seas disappear, the consequences ripple far beyond shorelines. They rewrite climates, extinguish ecosystems, and force civilizations to adapt or perish. The salt beneath our feet isn't just history, it's a mirror, reflecting the brittle balance between water and survival. Some of the most dramatic chapters in Earth's climate history weren't written in stone or ice, they were written in dust. Stretching across continents like pale, powdery blankets, Loess deposits are the silent remnants of ancient storms that once choked the skies. These thick layers of wind-blown silt, some towering hundreds of feet high, aren't just geological curiosities. They're archives of desperation chronicling eras when entire regions turned to dust. Take China's Loess Plateau, where deposits pile nearly 1,000 feet deep in places. Each fine grain tells a story. During glacial periods when ice sheets advanced, continental interiors grew colder and drier. Vast deserts expanded, their loose sediments vulnerable to the wind's whim. With no vegetation to anchor them, these particles took flight, swirling in storms so dense they could blot out the sun for weeks. When the winds finally calmed, the dust settled, layer upon layer, year after year, creating the golden cliffs that define the region today. But hidden within these soft deposits are darker clues, bands of red clay, evidence of even drier intervals when the storms grew fiercer and the land grew barren. Half a world away, the American Midwest tells a similar tale. The lowest bluffs along the Mississippi River aren't just scenic, they're the legacy of Ice Age droughts. As glaciers ground rock into flour like silt, meltwater rivers carried it south. But when waters receded during cold, dry spells, the exposed sediment dried into vast mudflats. Winter winds did the rest, lifting this powder and dumping it across what's now Iowa, Nebraska, and Illinois. The result, fertile soils that would later feed nations, but also a warning. Within these layers, scientists find abrupt shifts from coarse to fine particles, marking moments when climate flipped from wet to arid in decades, not centuries. What makes Loess so revealing is its fragility. Unlike hard rock, this loosely packed silt erodes easily, forming jagged badlands where rainfall carves deep gullies. These erosion patterns expose the deposit's internal story, revealing cycles of stability and chaos. In Central Asia's Tajikistan, for example, Loess cliffs show alternating bands of soil and pure dust, proof that grasslands briefly returned during wetter interludes, only to vanish again when drought returned. Even more telling are the fossilized roots and insect burrows found in some layers, remnants of ecosystems that thrived briefly before being smothered under the next dust storm. Today, these deposits hold urgent lessons. Modern satellite images show dust plumes from the Sahara crossing oceans, while drought-stricken regions like the American Southwest watch topsoil vanish on the wind. The difference is scale. Past Loess-forming events lasted millennia, giving ecosystems time to adapt. But human activity, overgrazing, deforestation, climate change, is accelerating desertification at a pace that mirrors the worst Dust Bowl eras in the geological record. The irony is that Loess, born of devastation, often becomes some of Earth's most fertile soil. Ukraine's breadbasket, China's agricultural heartland, both owe their productivity to these ancient storms. Yet the same fragility that makes Loess' rich land so productive also makes it vulnerable. When the rains fail and the winds rise, history shows how quickly abundance can turn to airborne ruin. The dust of the past whispers a simple truth: civilizations rise and fall on the whims of the wind. Beneath the ocean floor, locked in icy cages, lies one of Earth's most dangerous climate secrets: methane hydrates. These crystalline structures, where methane molecules are trapped inside frozen water, look like ordinary ice but burn with a ghostly flame if lit. What makes them so unnerving isn't just their flammability, it's their instability. These frozen deposits, scattered along continental shelves from the Arctic to the tropics, hold more carbon than all the world's known fossil fuels combined. And they're only stable under specific conditions. High pressure and low temperature shift that balance and the cages shatter, releasing methane, a greenhouse gas 30 times more potent than carbon dioxide, into the atmosphere. The geological record shows this isn't hypothetical. 56 million years ago, during the Paleocene-Eocene thermal maximum, something triggered a massive release of these hydrates. Sediment cores from this period reveal a telltale signature: a sudden spike in carbon isotopes paired with layers of oxidized iron that only form when methane bubbles through seawater. The result: global temperatures soared 5 to 8 degrees Celsius in just a few thousand years, a blink in geological time. Deep sea fossils tell the rest of the story. Bottom-dwelling organisms vanished as oceans acidified, while land animals shrank in size, adapting to heat-stressed ecosystems. Today, the triggers are eerily familiar. In the Arctic, warming seas are melting submarine permafrost that's been frozen since the last ice age. Off Siberia's coast, craters pockmark the seafloor where methane once trapped in hydrates has explosively escaped. Even more alarming are the methane chimneys detected in the Atlantic, columns of gas rising from destabilized deposits thousands of feet below. While most methane dissolves in seawater before reaching the surface, recent studies suggest some plumes are making it into the air, particularly in shallow Arctic seas where the water column is too short to filter the gas. The real wild card lies in feedback loops. As oceans warm, hydrate deposits at deeper, colder levels could destabilize, not from direct warming, but from subtle shifts in currents that bring slightly warmer water into contact with the seafloor. Once that process starts, it's self-reinforcing. More methane means more warming, which means more hydrate breakdown. Climate models struggle to predict the speed of this domino effect, but sediment layers from past warming events hint at the risk. Sudden methane releases that accelerated global heating far beyond what CO2 alone could explain. Yet there's a twist to this story. Some hydrate deposits are actually shrinking naturally, dissociating so slowly that microbes in the sediment consume the methane before it escapes. Other deposits are stabilized by saltwater infiltration, which alters their crystal structure. The key uncertainty isn't whether hydrates will release methane, it's how much, how fast, and whether we're pushing the system past a tipping point. What makes these icy time bombs so urgent isn't just their destructive potential, it's the precedent. The same sediment layers that warn of past methane catastrophes also show how long it took Earth to recover, tens of thousands of years. Unlike gradual CO2-driven warming, methane spikes can rewrite climates almost overnight. And while nature took millennia to trigger these releases, humanity's relentless warming is turning up the heat in centuries. The hydrates aren't just a threat. They're a mirror, reflecting how quickly we're rewriting the rules of a system we barely understand. Scattered through Earth's rock layers like cosmic confetti, tiny glass beads no larger than sand grains tell a violent story, one written in the split-second fury of asteroid impacts. These microscopic spherules, found from the ocean floor to mountaintops, formed when space rocks slammed into the planet with such force that rock vaporized into superheated droplets, then solidified mid-air before raining back down. But they're not alone. Alongside them often lies shocked quartz mineral crystals warped by pressures greater than any volcanic eruption, their atomic structure twisted into intricate patterns that only form under the extreme stress of a cosmic collision. Together, these materials form impact ejector layers, silent witnesses to moments when the sky fell. Take the KPG Boundary layer marking the dinosaur extinction. Beyond its famous iridium spike, this thin global stripe contains Tectite's glass beads flung halfway around the world from the Chixilub impact in Mexico. Some landed so hot they splattered like raindrops, leaving tiny craters in soft sediment before hardening. Others fused with debris to form bizarre, aerodynamic shapes called dumbbells and teardrops, frozen snapshots of their high-speed journey through the atmosphere. Even more telling are the spherules found deep in the Pacific Ocean, thousands of miles from the impact site. Their chemical signature matches Yucatan bedrock, proving they were launched on ballistic trajectories before plopping into ancient seas like a slow-motion meteor shower. But Chixilub isn't the only catastrophe recorded in glass. In Australia, the 3 billion-year-old spherule beds of the Barberton Greenstone Belt reveal impacts so violent they dwarf anything in human history. These layers, some over 3 feet thick, suggest asteroids up to 20 miles wide struck the young Earth, vaporizing shallow oceans and scattering debris globally. Unlike typical sediments, these spherules aren't mixed with other minerals. They fell in such overwhelming numbers that they buried the landscape in pure glass, like a snowstorm from hell. What makes ejecta layers so valuable is their precision. While craters erode or get buried over time, these microscopic markers persist. In North America's Atlantic coastal plain, ejecta from the Chesapeake Bay impact 35 million years ago forms a distinct layer traced from Georgia to New Jersey, a breadcrumb trail leading back to a long hidden crater now buried under half a mile of sediment. Similarly, shocked quartz grains in Scandinavia's sediments helped identify the previously unknown Mjolnir crater beneath the Barents Sea, proving a mile-wide asteroid struck there some 140 million years ago. The real urgency in studying these layers isn't just about the past, it's about calculating risk. By tallying ejecta deposits, scientists estimate kilometer-wide asteroids strike Earth every 500,000 years on average. Some, like the 3-mile-wide rock that left South Africa's Vredefort crater 2 billion years ago, could vaporize continents. Others might only trigger decades of nuclear winter. But unlike dinosaurs, we can prepare. Modern telescopes track near-Earth objects, while missions like DART test deflection techniques. Ejecta layers remind us that cosmic roulette is always spinning, but for the first time we're learning how to dodge the bullet. Stretching across North America like a shadow from the past, mysterious black layers of sediment tell a story of fire and ice. These dark bands, known to scientists as black mats, are more than just ancient dirt. They are forensic evidence of a cosmic catastrophe. Within their ashy depths lie nanodiamonds, microscopic gems forged under the kind of extreme pressure that only occurs during asteroid or comet impacts. Mixed with these diamonds is thick soot, the charred remains of continent-spanning wildfires so intense they turned entire forests to smoke in a matter of hours. Together, these clues paint a terrifying picture of what happened 12,800 years ago, when the world seems to have burned while temperatures plunged. The timing couldn't be more suspicious. This black mat layer appears precisely at the start of the Younger Dryas period, a sudden 1,300-year cold snap that reversed Earth's warming trend after the last ice age. As the mat spread across the landscape, the fossil record shows something equally chilling: mammoths, saber-toothed cats, and giant ground sloths vanishing abruptly from North America. Their bones often lie just beneath the black layer, as if some invisible force wiped them out overnight. At the Murray Springs site in Arizona, for example, Clovis spear points, the signature tools of early American hunters, are found embedded in soil directly below the mat, then disappear from the archaeological record above it. What could explain such synchronized destruction? The leading theory points to a fragmented comet exploding in Earth's atmosphere, similar to the 1908 Tunguska event but on a continental scale. The airbursts would have ignited forests from Canada to Mexico, while the soot and dust thrown into the atmosphere blocked sunlight, triggering the Younger Dryas freeze. Supporting this idea are impact craters like the one beneath Greenland's Hiawatha Glacier, dated to roughly the same period, along with platinum spikes, a metal rare on Earth but abundant in space rocks found in sediment layers worldwide. But the black mats hold even darker secrets. Some contain microscopic fungal spores that thrive on decaying animal flesh, suggesting landscapes littered with unburied carcasses. Others preserve acid rain residues, evidence of a poisoned atmosphere in the disaster's aftermath. Most unsettling are the glassy beads called melt glass, found at multiple Younger Dryas sites droplets of molten sand and rock that rained down after being vaporized by impact heat. These tiny time capsules record temperatures hotter than volcanic lava, frozen into spheres no bigger than a grain of salt. The debate over this catastrophe isn't just academic. Understanding how quickly climate can flip and how fragile ecosystems are to cosmic accidents holds urgent lessons for our world today. The black mats are a stark reminder that sometimes history's most dramatic chapters aren't written in stone but in ashes. Sometimes the most telling clues to Earth's catastrophic past aren't found in towering cliffs or gaping craters. They're hidden in parts per million, subtle spikes in elements that shouldn't be there. Take mercury, a metal so toxic it's nicknamed Quicksilver. In ordinary times, it barely registers in sedimentary rock, but drill into layers from certain periods, and the numbers skyrocket 10, 20, even 50 times above normal. These aren't random fluctuations, they're chemical smoke signals pointing to moments when the planet choked under volcanic fumes. The correlation is startling. Samples from the Permian-Triassic boundary, the layer marking Earth's worst mass extinction 252 million years ago, show mercury concentrations that mirror the Siberian Traps eruptions, a million-year volcanic frenzy that covered an area the size of Europe in lava. As magma tore through coal and hydrocarbon deposits, it vaporized mercury locked in the rock, sending poisonous plumes high into the atmosphere. Rain eventually washed this toxic fallout into oceans and lakes, where it bonded with organic matter and settled into sediment. Today, those same sediments serve as a planetary medical chart, with mercury spikes acting like fever lines on a thermometer, each one a pulse of volcanic violence. Yet mercury isn't the only metal telling these stories. Platinum group elements, rare metals like iridium and osmium, often appear in layers where they have no earthly business. The famous iridium anomaly at the KPG Boundary was the first clue to the dinosaur-killing asteroid impact, since these metals are abundant in space rocks but scarce in Earth's crust. Similar platinum spikes have been found in South African sediments dated to 12,800 years ago, fueling theories of a fragmented comet triggering the Younger Dryas cooling. Even more puzzling are nickel-rich layers in Australia's ancient rocks, which some scientists link to asteroid impacts so old they predate complex life itself. What makes these geochemical fingerprints so powerful is their precision. Unlike fossils or ash layers, which can be ambiguous, metal anomalies often have a single, unambiguous source. Osmium isotopes, for example, act like a cosmic GPS. Their ratios differ so distinctly between asteroids, volcanoes, and Earth's crust that scientists can pinpoint a disaster's origin with forensic certainty. In Caribbean sediments, a telltale osmium signature helped confirm the Chixilub impactor was a carbonaceous chondrite, a specific type of asteroid rich in organic compounds. But perhaps the most unsettling lesson lies in the patterns. When researchers overlay mercury curves with carbon isotope records, a proxy for ancient climate, they find an eerie consistency. The worst extinction events all share twin spikes of greenhouse gases and toxic metals. It's a formula for catastrophe. First, volcanoes or impacts deliver a knockout punch with rapid climate shifts. Then heavy metals and acid rain slow recovery by poisoning surviving ecosystems. The parallels to modern pollution are impossible to ignore, with one key difference. Those ancient disasters unfolded over millennia. Today, we're replicating the same chemical signatures in mere decades. These metal-rich layers aren't just scientific curiosities. They're time-stamped warnings written in a language older than humanity. And as we learn to read them more clearly, we're discovering that Earth's most violent chapters always leave traces, not just in the scars we can see, but in the invisible elements that linger like ghosts in the rock. Dig into the mud of any modern riverbank or scrape a sample from the ocean floor, and you'll find something unprecedented in Earth's 4.5 billion year history, a layer of human fingerprints written in plastic, concrete, and radioactive dust. These aren't just random traces, they're the calling cards of a species that's reshaped the planet so profoundly, scientists argue we've stamped our own chapter into geological time, the Anthropocene. Unlike past epochs defined by asteroids or ice ages, this one would be the first carved not by natural forces, but by the collective weight of human activity. Take the humble plastic bottle cap. Tossed into a river, it might seem insignificant, but multiply that by trillions, and suddenly these synthetic fragments form distinct layers in sediments worldwide. In coastal marshes from California to Bangladesh, researchers find microplastics embedded like artificial fossils, tiny, indestructible relics of our throwaway culture. Even more striking are the technofossils landfills packed with smartphones, car parts, and porcelain that will outlast most natural stone. Future geologists won't need to dig for dinosaur bones to study our era. They'll just sift through the petrified remains of shopping malls and iPhones. Yet plastics are just the visible tip of the Anthropocene iceberg. Drill into lakebed mud, and you'll hit a radioactive stripe marking the mid-20th century, the fallout from atomic bomb tests that scattered plutonium and cesium across the globe. This layer is so sharp and synchronous, it's become the leading candidate for the official golden spike of the Anthropocene epoch. Above it, other chemical ghosts appear, lead from decades of gasoline exhaust, nitrogen from industrial fertilizers, and a carbon isotope shift so abrupt it mirrors the atmospheric changes that triggered ancient mass extinctions. The debate isn't just academic. These human-made layers are accumulating at speeds that dwarf natural deposition. In places like the Great Lakes, sediment cores show that post-industrial sludge piles up 100 times faster than pre-colonial layers. Along coastlines, concrete and rebar now outweigh all living coral reefs and artificial geology forming in real time. Even our domesticated animals leave traces, chicken bones, bred to be meatier and more uniform than their wild ancestors, may fossilize as distinctly as dinosaur bones mark the Cretaceous. What unsettles scientists isn't just the scale of these changes, but their staying power. Plastic polymers could persist for tens of millions of years. Nuclear isotopes like plutonium-239 remain hazardous for 250,000. Future civilizations, or whatever evolves after us, won't need written records to know something extraordinary happened here. The rocks will scream it, but the most haunting lesson lies in the parallels. The same sedimentary tricks we use to decode dinosaur-killing asteroids or volcanic winters will one day be applied to us. When geologists of the distant future analyze our layer, what will they conclude? That we saw the warnings in the strata beneath us and chose to write our own catastrophe anyway? Or that we learned just in time how to rewrite the ending? The layers beneath our feet are more than just stacked rock. They're Earth's autobiography, written in the language of catastrophe and resilience. Every earthquake that cracks open a fault line, every volcano that rewrites a landscape, even the slow creep of tectonic plates, they all leave behind signatures in the stone, waiting to be read. What's astonishing isn't just the scale of these disasters, but how life persistently finds a way through the chaos. After the asteroid that wiped out the dinosaurs, tiny mammals emerged from the shadows. Following the suffocating anoxic oceans of the Permian extinction, new creatures evolved to breathe the revitalized waters. The planet doesn't just endure these upheavals, it transforms, adapts, and ultimately thrives. But here's the crucial lesson hidden in these layers. Survival isn't about brute strength, it's about flexibility. The fossils tell us that the most successful species aren't always the biggest or fiercest, but those that can adjust to sudden change. When climate shifts turned forests to deserts, some animals learned to burrow. When oxygen levels plummeted in the oceans, certain fish developed ways to extract more air from each gulp of water. The rock record is full of these ingenious adaptations, proof that catastrophe, while devastating, can also be a catalyst for innovation. Now, for the first time in Earth's history, a species holds the power to read these warnings before disaster strikes. We can track near-Earth asteroids with telescopes, monitor volcanic hotspots with satellites, and even test ways to deflect or mitigate these threats. The difference between us and the dinosaurs isn't just intelligence, it's foresight. Those ancient layers of ash and iridium aren't just memorials to past extinctions. They're guidebooks showing us the patterns of planetary upheaval so we can recognize the signs before it's too late. Yet knowledge alone isn't enough. The Earth's strata also teach us about consequences. The same mercury spikes that marked volcanic apocalypses in the Permian now appear in modern lake sediments from industrial pollution. The rapid carbon releases that triggered ancient hypothermal events. We're replicating them today by burning fossil fuels. The difference is timing. Nature took millennia to release what we've unleashed in centuries. But if there's hope, it lies in the fact that we're the first species capable of consciously altering our trajectory. So what's the next chapter in Earth's story? That depends on us. Will future geologists find a thin layer of plastic and radioactive dust marking a brief, reckless era? Or will they uncover evidence of a species that learned to match its ingenuity with wisdom? The answer isn't written in stone yet, but one thing's certain: the planet will keep turning, the layers will keep accumulating, and life, in some form, will endure. The real question is whether we'll be part of that future. If you've enjoyed unraveling Earth's epic saga with us, hit like, subscribe, and let us know in the comments, what geological mystery should we explore next?